This is section 3.2, part E, interpreting computer regression outputs. So the basic regression output for the NEA data from two statistical software programs are shown below. The one on the left is Minitab, the one on the right is from JMP. Now when you're looking at Minitab, you will have a column that says coefficient. This is where you will find your slope and your y-intercept. The one with constant is your y-intercept, and the one that's with the variable, the NEA change, would be your slope. They're also going to tell you your S value, and they will tell you your R squared. For the JMP, they're going to give you the exact same information, and this time the column is going to say estimate instead of coefficient, but they will tell you your intercept, and they will tell you your slope. They will also tell you your R squared and your S value. Now there is a lot of other information on that screen right now that we're not going to use now, but we will use later on. Students often have a hard time interpreting the values of R squared on their AP exam. So one piece of advice is just to treat this as a fill-in-the-blank exercise. From that last example, we can see that the R squared value is 60.6%. Remember, our X value is the NEA change, and the Y value in this case was the fat gain in kilograms. So we would write 60.6% of the variation in fat gain of kilograms is accounted for by the regression line. How well does the number of beers a person drinks predict his or her blood alcohol content? 16 volunteers with an initial blood alcohol content of 0 drank a randomly assigned number of cans of beer. 3 minutes later, a police officer measured their blood alcohol content. Least squares regression line was performed on the data. We have the scatter plot with a regression line, we have the residual plot on the right, and we have the computer output. So what is the equation of the least squares regression line? And we describe what the variables mean. So we have our coefficients listed. It tells us our constant, or our y-intercept, and it tells us the value with beers, which would be our slope. Now we can write this as y hat equals, or we can define our variables in our equation. So we can say our predicted blood alcohol content is equal to your constant plus your slope times the X variable. Now, we could have written this instead as just y hat is equal to your equation times X, and then you have to define your variables where X is the number of beers consumed and Y is the blood alcohol content. Or again, you can just write the variable descriptions into the equation itself. Now we need to interpret the slope of the regression line. We already indicated that the slope was 0.017964. And in this case, that's telling us for each additional beer that is consumed, we can expect the blood alcohol content to increase by 0.017964. We need to find the correlation. Now, we are given in our output that R squared is 80%, or we can write that as 0.80. To find R, we can take the square root of both sides, but remember we have the positive and the negative. So we know R is equal to plus or minus 0.894. Now your correlation is going to have the same sign as your slope. So if the slope of your line is positive, your correlation is also positive. Since our least squares regression line is going up or is positive, our correlation will also be positive. Is a line an appropriate model to use for this data? What information can tell us this? So if we are taking a look, the line does seem like it's appropriate because the residual plot shows a fairly random scatter of points about the horizontal line. Most of our residuals are going to fall between negative 0.03 and a positive 0.03 with just one outlier. So that tells us on average how far they are. We know based on our S value that our errors on average are 0.02 away. So the predicting the blood alcohol content is off by about 0.02 for every person. Now, we do need to put this back into context. That might be too large of a prediction error because the legal limit is 0.08 for being able to drive. So if you're under a 0.08, you're still legally able to drive. So if our prediction is off by 0.02, that's a quarter of that limit. If we look at our R squared value, we have R squared as 80%. So that means 80% of the variation in the subject's blood alcohol content reading is accounted for by the least squares regression line. What was the blood alcohol content reading for a person who consumed 9 beers? So we don't actually have the value itself, but we can find what we predict, and we know what the residual is. So from there, we can calculate what their actual reading was. So if we start by plugging in a value of 9 beers, we would predict a blood alcohol content of 0.149. Now, we can see from this residual plot that our predicted, which would be down here, is much lower than the actual reading. If we know how far away that is, which is our residual, we can use our equation. And we know that residual is equal to your observed minus your predicted. Based off that graph, we can say that the residual was 0.045. We know our predicted was 0.149. So from that, we can solve for y, and we can say that the observed blood alcohol content for the person who drank 9 beers was actually 0.194. So correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, you should be aware of their limitations. So here are some cautions. The distinction between explanatory and response variables is important in regression. Now, if you remember back to when we were talking about correlation, you can switch the x and the y values, and you would still get the same correlation. But if you switch the x and y values on the least squares regression line, you will get a completely different equation. Correlation and regression lines describe only linear relationships. So even though we can find a different type of regression line besides linear, the R value or the correlation only is actually valuable if this is a linear relationship. So you need to make sure that you always plot the data first to see if the correlation will actually be anything you need to use. Correlation and least squares regression lines are not resistant. So if you have any outliers on your data, both the correlation and your least squares regression line will be affected. Association does not imply causation. So just because two things are associated does not mean we can say there is a cause and effect. So for an example of this, if we take a look at the NEA change in the fat gain, originally we had the NEA change as our x value, the fat gain as our y, and we got our least squares regression line. If we reverse those and have our fat gain as our x or our explanatory, and the NEA change as the y or the response, we're going to end up with a completely different equation. Now those R squared values are still going to stay the same, which means the R values are still the same, but the equations are completely different. So let's look at an example. Do the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of young adults recorded the age in months in which each of 21 children spoke their first words, and then it took their results on an aptitude test. The data appear in the table below. You need to complete the 4-step process. Remember, in the 4-step process, you need to state what you're trying to solve, you need to come up with a plan, you need to do the calculations, and then you need to come up with a conclusion. So what we could come up with, our question could be, can we use a child's age at first words to predict his or her Gessel score? And how accurate will our prediction be? So for our plan, we can plan to start by making a scatter plot where we use the first words, the age at first words is your explanatory variable, and their Gessel score is the response variable. If the graph shows a linear form, then we can do the least squares lines, and we can do all of our calculations to find the residual, r squared, and s to see how well it'll do at predicting. For the do, we will actually make a scatter plot. As you can see from the scatter plot, we can make this a linear model, so we can make the residual plot as well. On that scatter plot, there are some blue points. Those blue points indicate that there is more than one child that have the exact same data. And from that, we can create our least squares regression line. On your least squares regression line, the slope suggests that for every month older a child is for their first spoken word, their Gessel score is predicted to decrease by 1.127 points. Since no child talks at 0 months, that y-intercept is actually going to have no statistical meaning for this problem. Now, if we do more calculations with this, we can find that the S value is 11.023. Remember, this is telling us on average how far off our estimate is from the actual score. So for the students' scores, which on this ranged anywhere from 40 to 140, our predictions on average were off by 11 points. The R squared value is 0.41, or 41% of the variation in the Gessel score is accounted for by the regression line. This means that 59% of the variation is not accounted for. So for our conclusion, we can use the equation that we've found before, that the predicted score is equal to 109.8738 minus 1.127 times the age of the first spoken word to predict a child's score on the Gessel test. Unfortunately, our prediction is not going to be very accurate. On average, our estimate is off by 11 points, and we know that 59% of the variation in the children's scores is not accounted for by the linear model. Now, if you notice, there are 2 outliers. Child 19 and child 18 are outliers in our graph. So let's see what happens with those outliers. Because we know these are not resistant, we need to see which one's going to affect the data more. So originally, with all 19 children in there, the R value was negative 0.64. And that is indicated, the least squares line is indicated by that teal line on the right. Now, if we remove child 19, which is an outlier in the Y direction, the R value actually does increase just slightly, and it is indicated by the red line on the least squares line on the right. The line is a little different, but it doesn't change much, and the R value doesn't change much. On the other case, child 18 is an outlier in the X direction. If you notice, all the other children are clustered together over here on the left, and child 18 is all the way to the right. So they are an outlier in the X direction. If you remove child 18, we are now going to end up with that dark blue line on the right, and you can see that line is drastically different than what we started with. We're also going to drastically change the R value for the least squares line. So we can see by removing child 18, we move the line quite a bit, because child 18's extreme position on the age scale is a big influence on our least squares regression line. However, removing child 19 has little effect on that regression line. So least square lines make the sum of the squares of the vertical distance to the points as small as possible. A point that is extreme in the X direction with no other points near it is going to pull the line. So we're going to say that that is an influential point. So it's an influential if it's an outlier in the X direction with no other points near it. Now we can have outliers in either direction. They can be an outlier in the X direction or an outlier in the Y. But the only influential ones are going to be if they're in the X direction. Let's look at another example of errors that we could make, and this is association versus causation. So a serious study once found that people with 2 cars live longer than people who own only 1 car. Owning 3 cars is even better, and so on. There is substantial positive correlation between the number of cars X and the length of life Y. The basic meaning of causation is that by changing X, we will bring a change in Y. Could we lengthen our lives by buying more cars? So the simple answer of this is no. You can't cause your life to be longer by buying more cars. What the number of cars is actually indicating in this is the wealth of the person. So a wealthier person is going to tend to live longer because usually they're better educated, they take better care of themselves, and they get better medical care. The number of cars has nothing to do with it. So there is no cause and effect between the number of cars and the length of life. So we cannot say any cause and effect. We can either say two things are associated together or that they have a correlation between them. So we can say that there is an association between the X variable, number of cars, and the length of life, Y, but we cannot say one causes the other. Now the difference between correlation and association, correlation can only be drawn between two quantitative variables. If we have one categorical and one quantitative, or two categorical variables, we can only say there is an association. So on the safe side, you can always say there is an association between the two variables.